Welcome back. So far, I have introduced you to cobots, its requirements and applications in the modern industry, ISO standards, its mode of operation, risk levels, risk assessment, and its reduction measures. So, the overview of this lecture is as follows. So, I will be discussing on evolution of force control, its brief timeline, transition in technology, fundamental technological difference, hardware difference, joint and the inbuilt actuator design, control schemes, position controlled robot as well as for the cobots, cobots mechanical arm design and the overall system of a cobot. So, let us begin with the timeline for force control. So, what exactly is passive force control here? So, passive control was a device which was fitted in between the gripper or any kind of end effector tool and the robot flange. So, that came in between. So, that was compliant. So, what happened if whatever the forces that comes on to the gripper or the tool, that is isolating the body of the robot to the gripper. So, that intermediate tool was giving it a passive compliance. It was a spring like a structure which is fitted at the end to take care of any collision or anything that is happening beyond the gripper. Whole of the robot was still stiff. So, this is one of the earliest method of doing that. That was done by Grumey MIT feed forward teleoperation system and by the Navis. Okay, and then later on in 1975 rest and pedestal force sensing came in. That is where we started using end effector force torque sensor instead of these passive compliance, and whole of the system became active. That means live forces we are taking into account, we are creating it in a closed loop, and we could desire for a particular force. That was not possible in case of passive compliance device. Now, in case of active compliance, we can maintain a particular force at the end effector or the torque at the end effector. So, this is where we started with active force control in 75. Then Whitney introduced active control for of first order, that was known as admittance control here. Salisbury introduced the stiffness controller, which is again trying to make the robot behave like a spring after the end effector, after the flange actually, to handle any external things. Okay, so that was again an active force control only, but it is in a closed loop. And then in 81 actually Mason, he provided with hybrid position force control, that is a hybrid of position as well as force control. Robot can go to a particular place and handle the forces as well. So, again similar one was given by Raybert and Craig, that is there in the textbook also. He implemented a hybrid force control technique with standard industrial robot, where he partitioned the workspace into orthogonal spaces of force and position control. That was his contribution in 1981, and again Hogan introduced the impedance controller. This is one of the benchmark introduction in force control, where impedance control was introduced, and even in current days all the cobots they use impedance controller of advanced implementation. Okay, and then a series of things came in 1988-89 when robust controller external control loop that was given by Shutter. He again utilized a force control that is sensed through the wrist force torque sensor and created a closed loop which is reported even by this. So, it is an advanced version of this that was reported by Shutter, that uses a standard industrial robot and does the force control job. Okay, and then he first proposed the parallel force control that was given by this, and then hybrid impedance came in, stiffness is here, hybrid again. So, you see a set of reporting started coming in 1988-89, and again 1992-93 another huge set of controllers that came in. Okay, adaptive control, admittance control, explicit force control, multiple impedance control. Here this is again an important one, that is the direct drive joint, which was later on adapted by ABB also. So impedance control of direct drive joint. Direct drive means there is no gearbox in between, the link was directly coupled to the high powered motor which is there, and then it became very much compliant enough because there is no gearbox, it was back drivable, and torque reflectance ratio was too good. Okay, so this is one of the major benchmark, so that is there. And then Cockewell, he came up with multi-manipulator parallel force position control, intelligent control also is reported here. From here you see quite a lot of papers started coming in intelligent control. Okay, and then 1994 some steady state approximation came in, passivity based controller, force based impedance controller, and multiple control approaches, PD and PI, PD for position, PI power for force control was used. Okay, non orthogonal subspaces, hybrid controller was given. Okay, detailed environmental model is developed here. Okay, and then Aguilas, he finally came up with the direct drive joints for ABB robot, that was a hybrid controller which was implemented. Moving further, collision simulation of virtual objects, that was taken into account, admittance feed controller, resolved acceleration approach, model based generalized impedance controller came in, rotary series elastic actuator and disturbance observer came in here. This is again a very good model which was there, and DM square model when parallel motors were used at a joint and with a high and low frequencies, that was given by Khatev and team from Stanford, that was given. That is again a very important thing which was given. Khatib came up with compliant multi-contact humanoid also when multiple contacts are taken into account. Okay, and then sliding mode impedance controller, apart from various other impedance controllers, sliding mode control which was much better, that was reported by Chen here. Direct drive with disturbance observer, again it came in. Okay, neuromechanical control, non-linear bilateral adaptive control. So you see these are the controllers with non-linear and adaptive neural ANN kind of algorithms were introduced here. So you see now things are moving towards intelligent approaches and sensorless realizations started in. The direct drive with disturbance observer technique is one of them. Intrinsic sense of touch, intuitive PHRI, this is the recent reporting which uses standard torque sensor which is already there at the joint. They used it to detect the touch without having a tactile sensor. So it is a kind of sensorless realization of tactile sensor in the robot. Okay, I will show you the video of this also. So and then you see active research is going on in force control using AI/ML based approaches, deep neural networks, reinforcement learning, and those approaches are now going on. Okay. So what we see, the transition in technology started with passive, went on to active with different sensors at the joint, at the pedestal of the robot, even at the wrist of the robot. So different sensors are used and use that in a closed loop to create the forces at the end, at the joint, that compliance are established. Various algorithms came in with stiffness, impedance, admittance, and parallel hybrid force control was reported. And finally we started doing with intelligent machines that used adaptive and robust learning based approaches here, and now it is on sensorless realization, and hardware developments are becoming very popular now. They are trying to make things very compact and very much implementable for all these algorithms which were there. So combination of technologies are also there. Let us say it can be a combination of active and passive controller. Let us say a robot was made active controller to control the joint forces and joint torque, whereas end effector you can still have a passive compliance spring like structure. Okay, and you can have multiple algorithms with active sensing. Robust adaptive can be made along with impedance controller. even sensorless control like tactile sense can be done with admittance thing. Okay, so these technologies are also used in combinations. Okay, so let us just watch a small video here which will elaborate upon the transition that has happened. So in the left side video you see there is a compliant structure, passive compliance. Okay, that's a ATI device, and the right side of it you see you have a video that shows a wrist sensor with gripper that comes at the end. So in between the robot flange and the end effector you have a 4 sensors sandwiched here, so that you create a closed loop and make things compliant. I am able to handle the robot using my finger touch. Okay, this is again a dynamic current limiting when human robot interaction is shown, and the right side you see it is having collision and still the joints are compliant. In a way I am trying to limit the joint torques which can be delivered out of some current. So essentially I am limiting the current at the joint, and I am able to make the robot compliant. So even in industrial robot, joints can be compliant, but this is only for the safety purpose, not for a precise force control. See, I am able to move the joint one by one. So each and every joint has limited current that can flow through it. Even the base joint, which is one of the heaviest joint which is there in the robot, I am able to move it. So this is reported in one of the publication that I have shown below. Active compliance. So this is the most modern cobot that you see here. It uses active compliance. It has joint torque sensor at each of its joint. All the joints it has it. So with this impedance controller and end effector force control, you can do things like this. So whole of the robot is compliant, not just the part of the robot which comes after the wrist is compliant. Even before that, whole of the link is compliant. This is multiple simultaneous contact points which is reported. This is the latest one in 2024 it has come. It is an example of learning sensorless based approaches, when a person is able to detect the touch even on the surface of the robot's body. So precisely it is trained using the sensors which is already there in the robot, and it can detect the sense of touch. Okay, so touch sensor capability is reported, and even the end effectors there, that is compliant, joints are compliant. You can even have something at the end or anywhere on the robot, you can write something and it recognizes it as a character if you are writing it. So it's a complete intelligent thing which is reported now. Okay, so this is where we are now. This is one of the latest thing which is there in cobot. So apart from having whole of the robot compliant, now it is also having tactile senses. It is becoming very near to human nowadays. So these are some of the videos that I have shown. So what fundamental technological difference which is there? So let us start with a small link like a pendulum with mass m, link length L. So center of gravity is situated here at L/2 distance from the top. This is the axis of rotation, theta is the joint angle, tau is the torque at any instant of time. So you see mg is the force which will come here, g is the acceleration due to gravity. So this is the model I will use to explain the fundamental difference. So normally traditional industrial robots, they run with position controlled servos. That means at the joint they have encoder or the joint sensors, joint angle sensors, that continuously monitors the joint angle, keeps it in a closed loop and creates a PID on top of it. So that works with joint angular error. So this is the joint angular error multiplied with Kp, that is the position gain. This is velocity gain. So this is joint angular velocity error, desired versus actual. So left one is the desired, right one is the actual. Same here, this is joint velocity error multiplied with Kv, joint angular error integrated over a period of time multiplied with Ki, that is the integral gain. So this essentially is a PID controller that provides the torque. So torque is an outcome of joint angular error. As long as the error is there, it is going to provide continuous torque to the robot joint. So what happens if there is any obstruction anywhere over here? This continuous torque will provide continuous current to the joints, and the motor may get damaged or too much heated up. Okay. So any obstruction creates a huge torque arising out of the integral term. So if the error remains there for longer amount of time, so error integrated over a period of time creates a huge amount of torque and current at the joint. Okay. So this is bad for the robot joint, that is for the actuator or the motor if it is there. Okay. And it applies its full effort to reach to the commanded position, that is the desired position. So if there is any obstruction on the way, so the robot may get damaged, or the tool will get damaged, or the environment will get damaged, motors may get damaged, so something wrong will happen. Okay, so it applies its full effort to reach to a place, because it only works with joint position error irrespective of the torque which is going to come at the joint. It does not bother about the torque. Okay. So whereas in case of cobots, it runs with position controlled servo with torque limits. So it also cares about the torque which is here. It continuously keeps the track of torque by way of measuring the current, or sometimes it physically has a torque sensor, strain gauge torque sensor, or maybe encoder difference kind of torque sensor. It is there at the joint. With that, it comes to know the actual torque at the joint, and it precisely controls the torque, or sometimes it limits the torque. Both are equally okay, purely using the torque controlled servo actuator. So you can continuously keep track of the torque which is at the joint and create a closed loop. Okay, so joint torque is calculated using inverse dynamics equation. Mind it, this equation we will be deriving while we will be doing cobot dynamics, and even this PID controller and all we will be discussing very much in detail towards the end of this course in control, force control thing. Okay. So yes, this torque goes to the robot joint corresponding to the joint acceleration, joint velocity, and joint angle that you want. Okay. So this is the torque that should go to the joint. Even when the robot is stationary, this first two term goes to 0, only the last term, that is due to the gravity torque, continuously has to go to the joint in order to stay there, because brakes are not applied and the robot is free to swing like a pendulum, okay, like a serial chain pendulum. So in that case, this much of torque continuously goes to the robot. So now with this torque, if it is in closed loop and robot is made to run only with the torque, what happens? So any torque in excess due to any obstruction is limited. In order to go there, how much torque you need is mg sin theta into L by 2. That much is the torque is required to be here at this angle. So let us say robot started from here, it started going like this, and in between it had a collision. So what happens? It demands more torque than it is required to be there. Okay, so that excess torque this robot cannot provide, or a little bit of higher side it can provide. So in that case, the torque error is very less. The desired torque and the actual torque is difference, and then in that case, because it cannot provide that much of torque, the robot stops there, and while stopping there is very small amount of current that goes to the robot joint to maintain that position, okay, and that makes the robot safe, the motor safe. And the collision, because it is not servoing for the position, it is not applying its full effort to reach to the commanded position. Okay, it only applies the amount of torque which is required to go to a particular place, not to the full effort. Okay. So the excess torque beyond the dynamic torque is governed by the desired end effector impedance or the programmed joint stiffness. So how much the stiff I want my joint to be, how much end effector force that should come that determines how much torque I am going to feed it with. Okay, so this is why these cobots are very safe, and this is the fundamental driving difference of a cobot and traditional robot. Okay, so this is how the joint is built for standard traditional positional servo motor. So the motor which is here, it is shown here, this is a DC, it shows a commutator also, so it is a winding motor with permanent magnets here. So this is a kind of DC motor, permanent magnet DC motor with a commutator. So this is the motor part of it, this is the gearbox, these are bearings and the output shaft. At the rear part of it, it has an encoder here, power cable and the encoder. So essentially it gives the feedback of joint angles through the encoder. Okay, so only position is taken into account. What else you can read is the current that flows through this actuator. So you can take care of the current also, but yes, you cannot precisely control it because there is a gearbox here that has used lot of friction and the noise. So we'll talk about this. So the actuator, they run with joint angular position feedback given by the encoder. The output shaft uses a high gear ratio for transmission to increase the torque output and to reduce the angular speed. Reducing the angular speed make it more controllable. Okay, so this is the reason for putting a gearbox over here. It enhances the torque and reduces the speed. It has a very poor load side, that is this side where the link is fitted, to the motor side torque reflectance. Okay, so if there is any disturbance that comes here because of gearbox that is here, you see very little change in the torque that is felt to the motor shaft, and that is poorly reflected by the current that flows through the power cable of this motor. So you can detect the huge change, but definitely not a small change. That may be because of any human collision or maybe small obstruction if it is there. So you can take care of current only to ensure the safety. Okay, so any huge current surge, you can apply the brake or you can switch off the motor. Okay, so this can be taken care of, but definitely you cannot precisely control the current to control the torque that comes here. So this motor itself doesn't support this to be in a cobot. Okay, it can only do position control. Next, it uses current based on torque limits only to ensure the safety. High gear ratio makes the joint non-back drivable. So these joints, you cannot apply torque here to drive back the motor. Okay, it becomes back drivable due to huge amount of friction which is here, and they are not compliant to any external torques or moments that acts on the robot joints or at the robot tip or somewhere on the robot. Okay, so this essentially the hardware is different. Now coming to the hardware of a cobot. So how does it look like? It has a position sensor, it also has a torque sensor. So it has both. It can take care of torque in a closed loop as well as it can form a closed loop around a position, so that it ensures precise positioning, taking care of the torque also. It has a low gear ratio harmonic drive which is here, or sometimes it is direct drive also, power converter unit, microcontroller board which is here that creates a local closed loop also, power controller board is here. Okay, robot drive with position sensor is here. So whole of this set also, you see it is center hollow, so that you can pass through the wires from within. Okay, all the wires, they pass through from within the robot arm. So this is the beauty of having such a nice actuator. So this actuator can run with joint torque and position feedback both. The output shaft uses low gear ratio for the transmission. The gear ratio of this is very low, or sometimes it uses a direct drive coupled to the output shaft. There is no gearbox at all, so it makes it completely back drivable. The joints are back drivable. This allows manual guidance for the ease of programming, lead through programming and those. Okay. it runs with commanded torque input that are computed by the Cartesian or the task space compliance that you want, or the joint compliance requirements. How much stiff your robot should be, depending on that you calculate the torque, you put in only that much of torque to the joints. Okay. So, finally, you also can monitor the position to ensure precision and safety. Safety against free fall, because you are continuously servoing the motor, brakes are released. If at all anything, let us say you have provided less torque to be there, it can freely fall like a serial chain, like a pendulum. Okay. So, it can detect free fall if you can continuously monitor the joint velocity, any over speeding or joint software limits. So, you do not want a joint to rotate beyond certain limits, plus or minus, you can stop that. So, these are the reasons why you are also using a position sensors. So, it has a dual loop of torque as well as position, velocity, everything. We will talk about that also. So, you see this whole of this package goes here. So, you have first link that comes here and the next link goes here, and in between you have whole of that package. This is shown nicely here when both the links are disassembled, and this is there in the blog which I have put here. Okay, you can go through that. Okay, so if you disassemble whole of this cobot joint, over here it is a Somanet Circulo which I have shown. So, you see it has a frameless BLDC or BLDC, that is brushless DC motor, or permanent magnet synchronous motor if it is AC motor, AC or DC kind of cobot. So, this is a frameless motor. You cannot have a packaged actuator like industrial robots. Okay, you cannot put it like that, because this whole of this system has to be very light in order to reduce the inertia, so as to control any collision damage. Okay, so these motors are inbuilt inside the robot casing. The link itself you saw here, link itself provides the housing for this assembly. Okay, so that is why frameless motors are used. Stator and the armature set is there, that goes here, that is here, and then motor shaft is designed on top of this harmonic drive, that also goes to the casing, and finally the output shaft is here. You have encoder here, you have encoder here. Again, two encoder difference can be used to find out the torque which is there at the joint. So, this can be used also, input and output side of the gearbox. If you know the stiffness of the gearbox, you can calculate the torque based on the encoder readings. This is a primary way of doing it, but also it has a live torque sensor which is based on the strain gauge or different technology maybe. Okay, so that is always there. So, this is IO connector, digital to analog connector, and EtherCAT, that is a kind of industrial communication which is there to communicate the data to and fro from the robot joint. So, this joints, so all the commanding is done to this. Okay, then you have a brake actuator which is here, power electronics, and the local controller which is here. This controller ensures the command to be executed, the amount of torque or amount of current that you want to go to the robot, or to the position closed loop. All the loops are closed here. Then the external PC based controller takes care of the algorithms and the kinematics. This motor itself has a local closed loop that ensures the position and the torque. Okay, so you have accessories like bearings and all, drive casing is there. So, whole of this assembly is there in the cobot single joint. Okay. So, now the traditional industrial robot, they have joint position controller. It used to run like this. You see, for the traditional robot, what you want is the end effector position. We use inverse kinematics here. We will talk about each independent block later on in our course also, like inverse kinematics, forward kinematics. We will be dealing with this. For now, you just get to the philosophy of this control. So, for the given end effector position, you calculated the joint angles. Actual angle is fed as a feedback from the joint, and you calculate the error in angle goes to the position control, and finally what you get is a reference velocity here. That velocity is compared with the actual velocity. This is the speed controller. This generates a reference torque here. This torque and the actual torque is compared and error in torque is calculated. That finally sends the current to the actuator. Okay, and finally the actuator provides the torque and that goes to the robot system. Output of the robot, you have a velocity sensor, joint velocity sensor and the joint angle sensor. So the velocity may be derived out of the joint angle only. So these two are the feedback lines. So this is how this whole closed loop is working. So it is a cascaded controller where input is the joint angle essentially. So this is my actuator. This is the system which calculates based on the kinematics if it is there. So based on the kinematics, it does inverse kinematics, calculates the joint angle, and finally whole of the closed loop works on the joint angle feedback. Okay, we don't have much control over the torque, only we can limit this torque if at all there is any torque limiting feature which is there in the actuator. So this is the structure of the controller. Okay. Now if at all you want to do force control with such kind of actuator, a robot which is built with this kind of actuator, so this robot demands what is the joint angles. So this is ensured by the joint angles are ensured by the joint actuator. So joint angle is commanded and robot goes to any XY position and you have what is a wrist force torque sensor. You get the feedback of force here. Okay, so this is an external loop of force that comes here. Calculate the error in force, goes to the force control PID loop that calculates the desired position depending on the force error. So this requires an end effector or the wrist force torque sensor. So whole of the robot is stiff. At the end you have a force sensor. You can control forces after the wrist, that is at the tip of the tool maybe. Okay, so that is where you can control the force. So this is how it works. This work is reported here using external control loops in IJRR 1988 reported by Shutter. So this is how external force loop can be used to control the forces at the end effector using standard industrial robot that uses joint position control servo. Now next, so if at all it is a joint torque controlled actuator, so what it has basically, it can take in the commanded torque also. Okay, so torque is commanded here, checked for the any maximum limit. If it should not accept that, multiplied with 1 by kt, kt is torque constant, it calculates the current reference. Current again it is checked for maximum current that can go to the motor, so it is limited here, and then this current is finally controlled here, and accordingly the PWM inverter calculates the phase input that finally goes to the motor. It can be a BLDC motor or it can be a PMSM motor depending on that. So essentially it is controlling the current based on the torque input. Okay, so torque input, that becomes the torque desired, and finally that torque is achieved at the output of the motor. It also keeps track of the joint angles for internal purposes to ensure the actual position if it has achieved or not for other purposes, maybe for the safety and free fall detections. Okay, so entire details of this again will be covered while I will be discussing actuator in the next module. Okay, robot control and force control, those things when I will be discussing in those sections, I will explain very much in detail this. So philosophy here is you can command for a torque and you can achieve a particular torque. In between you can control the current. This drive can be of any type, it can be a DC motor also. Okay, so this is the control scheme for torque controlled actuator that goes to the cobot. Okay, so the control scheme for using such kind of robot. So this robot accepts torque at the joint. So that means this robot should be built with the actuator that accepts the torque command, not like a position command as we saw here. This robot was accepting the position command here. Okay, so now this torque goes here, and you see this is given by Raybert and Krag in 1981, that shows hybrid force and position control. Basically, in this controller, the task space of the robot was split in two, that is position and force control or orthogonal spaces. Let us say if it needs, it can put force control along this direction, and remaining two direction it can have position controlled. Okay. So this is a compliance selection matrix that detects the end effector interaction. Accordingly, this is the position command which goes here, and this is the force command that comes here, and compliance selection, actually if it is selected for one of the axis, if it is force or position, other one should be the position. Okay. If it is force over here, it is position over here. So you have a position controller here, and this is the force controller, and together it sends the torque to the robot, and robot runs. So there is a feedback of position, feedback of the forces. Forces here I mean force and the moment, and for position I mean here is the position as well as orientation. So it has two orthogonal spaces, one for the force, other one for the position. There are many such schemes like stiffness controller, admittance controller or impedance controller which are there that can do such things, and very much in detail again I will be covering in the force control module. For now, the philosophy is you can control the end effector, that is the task space forces as well as position for two different inputs along those two orthogonal directions. Okay. So this is a kind of a scheme which is used to do that. Okay. And this uses a torque controlled actuators. Okay. So the robot is made up of those actuators. Okay. So now cobot mechanical arm design. So what it goes to design such arm? It should be a lightweight arm. Generally it is cast with aluminum, composites, plastic structures for safety against collision with environment or human around. So the surfaces are very soft because of these materials. It also has concealed wires because nothing should get entangled with those wires, because humans are around. No, it can catch up a human organ or maybe a cloth which the person is wearing. So that should not happen. So no external wiring is allowed, electrical or pneumatic wiring. Soft and rounded edges. So because of the material it is soft, it also should have a design which is very much aesthetics, and it should be rounded edges, so nothing can get trapped into the edges of the robot as well. So it looks very better aesthetics. In case of anthropomorphic robot, it also should look like humans, so they are even more aesthetically better. Inbuilt self calibration system, no external mechanical stops are there, they are inbuilt to the robot joint. Okay, so again those can have edges and places where something can get stuck. Okay, safe design is done so as to avoid any pinching, trapping hazard in compliance to ISO 13849, that is the machine safety standard, and ISO 10218, that is the industrial robot or robot safety standard. Okay, electromagnetic compatibilities should also be there as per IEC 61000 against immunity and emission. Okay, because this motor should work ruggedly even in case when you have external emissions, if at all it is there due to any transformers around. So this structure is such a safe structure. Okay, it should not fail because it is very near to the environment where humans are around. Low vibration and noise, we prefer even in case of industrial robot they remain within 65 decibels, but if it is in for a medical purpose it should be less than 40 decibels. IP rating IEC 60529, depending on the application to application. Ingress protection rating is adapted, how much water and dust it should protect against. Okay, so those are taken care of, and provisions for heat dissipation, because humans can touch the surfaces of the robot. So that should not become very hot so as to make it dangerous. That is quite possible in case of industrial robot, but in case of cobots the surfaces are not very hot and person can touch it. So provisions for good heat dissipation should be there. Okay. So overall, while taking care of all these, this definitely makes this system quite complicated and it becomes very difficult maintaining the robot, but still care is taken so as to make the robot very much accessible. All the joints are accessible so that you can do maintenance and all. Okay. So now overall the cobot system is made up of these. So basically the arm, where you see all the joint assemblies are there. Okay. So cobot arm includes all the 6 or 7 servo drives depending on the degree of freedom of the robot, motors, gearbox, encoders and end effector tool mounted at the end. Okay. So this is the arm. It has a teach pendant which has buttons for motion control, play, pause, stop, input and output control, jogging, emergency stop, tri-state enabling switch for the safety. That switch has got 3 states. If you press it hard, it is off. If you release it, it is off. In between, it is on. That is a kind of tri-state enabling switch which is there. 6D joystick which is here, emergency stop you can see here, play and pause button is here. Okay, touch screen interface may be there for easy programming, calibration, file handling, number of programs that are stored in the robot controller you can see here, you can control that. Administrative task, USB port may be provided to copy any programs to this system. Ergonomic gripping with straps are there and it is lightweight. Okay. Again the hardware controller which actually has all the controllers for the robot, that is the kinematics, inverse kinematics, everything is here. Okay. Kind of impedance controller is here. It is not at the joint. At joint has a local loop for current and torque positioning thing only. Okay. Rest of the thing comes here and it is very much like a PC which is there. So it has a real time operating system, communication, network interface for the robot and the PC, robot control software, input output, storage, SMPS, power management board for the controller, dedicated safety card, memory cards, battery, brake resistors, switches, fans, etc. So all those things goes to this hardware controller, and at the external to it there is a desktop or a laptop PC that is used to program this controller. So it has a programming integrated development environment. Programming environment can be ROS, it can be C#, it can be Python, it can be anything. It can have a dedicated API given by the robot manufacturer which you can use it with any programming language. So it has a USB, a LAN for communication, interface to the robot hardware controller, that is this one, a standard hard drive, memory, motherboard and the processor. Okay, so this all makes the complete cobot system. Okay, so industrial variants, they use field buses for safe and faster communication, input and output. Standard robot languages are there, GUI, and the platform is very much rugged. Okay, so this is a quick reference to what all I have discussed. So it has links for the torque sensor, that is a sensor drive link that I have explained here, I have mentioned here. This is not an exhaustive list, you should not just go by this, you can work on the internet and find many such drives, torques are there. So servo drives, it is Synapticon I have mentioned here, Somanet Circulo. A frameless motor, it can be a Kollmorgen or Beckhoff kind of BLDC motors also you can put, but I have put a TQ group. that is a robot drive which is also used by KUKA Aiwa earlier. Okay, so that I have mentioned. Harmonic drive that I have mentioned here, you can use Harmonic Drive AG, that's a German company that I have mentioned here. But there are many like Shimpu company of Japanese company are also making harmonic drive. So this is not an exhaustive list again. So thanks a lot for this lecture. In the next lecture, I will be covering constrained motion tasks, distinguishing features of a cobot and those aspects.